Welcome to ECEN 215 Principles of Electrical Engineering. Today we're going to talk about DC equivalent circuits and what that means and how to transform a complicated circuit into a simpler circuit that we could use for other purposes. So let's go ahead and get started. So what is the point of an equivalent circuit? Why do we do this? Well, the idea is we have this complicated circuit, things that you've seen even a little bit so far, even though I wouldn't even consider those overly complicated. But if you have a circuit that is full of different resistances, obviously in future lectures we can see this is going to expand beyond resistances. It could be inductors, capacitors, some complicated circuit. Um, um, and we're going to replace that in the case of using the ones with resistances. A circuit is just simply a power supply, just simply a voltage source, and a series resistance that has a resistance that is computed as well. So it's going to have some voltage and some resistance. So this is a complicated set of circuit elements. So we could have a power supply with a series resistor, another resistor here. You could have a current source, you know, some set of resistors like this. I mean, something that looks pretty convoluted. Um, just draw something really bizarre. You could have something like this is the set of circuit elements, and we want to turn this into this simple power supply and resistor. Why you would want to do this is you could actually have multiple stages of a design. For instance, if you have, say, an instrumentation system where you have a set of different pressure sensors um, or temperature sensors, and you're going to have a stage one where the sensor actually connects and gets amplified, and then you have another filter stage where you're going to clean up the signal, filter out noise out of the signal, so on and so forth. So usually when you design a circuit system dealing with an instrumentation, you have multiple stages that you go through. Well, if you're simulating those stages and doing an analysis on the stages, it's nice to break the stages up into, instead of one big circuit, you have a couple mini circuits. And then what you do is you take, the first part of the circuit, model it, turn it into this Thevenin equivalent, and then use that to be the input for the second stage. You're actually going to see this used in a future lecture. So that's why we do this. So there are two types of equivalent circuits. The main one we're focusing on is a Thevenin equivalent, but there is also the Norton equivalent, which is pretty much the exact same thing. The only difference is that we change the voltage power supply to a current power supply. So that's one of the key differences, obviously, is those two things. And then since we went from it being a series resistor, and now we are current supply, the resistance changed and it became parallel. And you can go back and forth between these two simply with Ohm's law, because we know that I is equal to V over R. So if you know RT, if you do the Thevenin equivalent analysis, which is the next step we're going to be showing in converting your circuit, if you know RT and VT, from your analysis of getting this circuit, then getting the Norton equivalent is just simply solving for IN and just changing the configuration of the circuit to be a current source now with a parallel resistor. So that's all you have to do. If you're given the Norton equivalent, then you can simply get the Thevenin equivalent by changing the circuit configuration to a series resistance and then using the Norton equivalent current source and RT. So it's just simply using Ohm's law to go back and forth between the two. So now let's ask ourselves, what are the steps that we need to go through to convert a circuit to a Thevenin equivalent? So we have this little simple circuit here, just simply a little voltage divider. We have a power supply that's 15 volts DC. We have a 100 ohm and we have a 50 ohm. and we want to turn it into the Thevenin equivalent. So we're going to go through those steps and see what's involved in doing that. So now let's talk about the steps to actually get a Thevenin equivalent. So we're going to start with this simple circuit here, just simply a voltage divider. We have R1 and R2, and this power supply 15 volts. And we start with the fact that R1 and R2 from the previous circuit we were looking at a moment ago has 100 ohms and 50 ohms. So we're going to just start with that. So if we use mesh current circuit analysis, even though we have the voltage divider formula, and I'm going to show that in just a second, but just to show that you can do this with any analysis method, we are looking first for the open circuit voltage here on these two terminals. So we're looking for here and here. So this is the voltage divider formula that would get us that. But just to show you the method, doing the loop analysis, we end up with minus 15 volts. Starting here at this power supply, we're going this direction. We're following the current this direction, the loop current. So minus 15 volts plus the voltage to drop across R1, which is R1 times I1, this current, plus the voltage to drop across the R2, which is actually VOC. That's what we're actually interested in, VOC, which all of this must be equal to 0. And VOC is simply, in this case, using I1 times R2. So if you solve all this back, make this all equal to each other, you'll end up with this formula right here. So that's where all of that comes from. And of course, I said this is just simply the voltage divider, which if you have a circuit like this, you can automatically go to this formula. VOC is equal to VS times R2 over R1 plus over R2. And you end up with VOC is 15 volts, 50 over 150 ohms, which is equal to 5 volts. So VOC is simply 5 volts. So we got step one. So what do we need to create a Thevenin equivalent? We need the open circuit voltage for here, which gives us our VT is equal to 5 volts. So that's it. So half of the battle is won here. We have two steps. We have to get the the Thevenin equivalent voltage, which is the open circuit voltage across the terminals we're interested in, and then what is known as the Thevenin equivalent resistance. And there are actually two ways to do that. So we're going to show both methods. So the first way to get this is solving for what is known as the short circuit current, and then using that to back out the Thevenin resistance. So here, if you noticed, we have our circuit here. There's our two little terminals, A and B, if you will. And we've connected a short circuit. We literally have connected a wire between these two. And of course, we now have changed the dynamics of the circuit. And what we're going to use to determine this Thevenin resistance is we're going to use ISC. We're going to determine what is the current going through this short circuit. So we've reconfigured our circuit, and we drew it this way. And now we're going to do an analysis on it and solve for ISC. So for the first step, we're going to look at what is going on here. So ISC, because there's going to be since we got a short here, the voltage to drop across R2, this right here, is equal to 0 volts. Why? Because it's got a short across it. This is equivalent to us putting in a 0 ohm resistor here. So just real quick, because there's going to be some test questions actually dealing with this. A short is simply a 0 ohm resistor when it comes to analysis. So you could replace this wire mathematically. You could still use Ohm's law, put a 0 ohm resistor in here, and then solve, R2 being 50 ohms with a 0 ohm resistor in parallel. Well, 0 times 50 is 0 divided by be 50, so 0 plus 50, and of course you end up with 0. So the overall resistance of this branch right here is equal to 0 ohms, which means that there is no current flowing through this 50 ohm resistor. The voltage drop across it is 0 volts, so there's no current flow. all of the current now is flowing through the short circuit, which conceptually makes sense when you think about it. So now that we have that, all we have to really do is solve for the current going through R1 right here. If we know that, because if we know that, then we know ISC. So all we have to do is figure that out. Well, that simply is just the 15-volt power supply across R1, which just happens to be 100 ohms. So if we do that, we end up with 15 volts over 100 ohms, which is 150 milliamps. So now that we know this, we can now back out what RT is, and we get RT by using VT that we had a moment ago, which was 5 volts, over the short circuit current, which happens to be 150 milliamps, and we end up with 33.3 ohms. Notice the change here. This isn't VS, this is VT. So we used ISC, which was determined here, and all we did is took the 5 volts that we determined before, the ISC that we have from computing this analysis by doing the short circuit analysis, and we get to 33 1/3 ohms. So this method especially works with circuits that can kind of get complicated, but there is another way of doing this. I actually prefer the second method a little bit for more or less the standard circuits that we see, because it's since we've done all of the analysis for resistor analysis that we did the other day, where we had parallel series resistors, it works quite well. Both of these methods work. So it just really depends on which one you want to use. So this is method 1 for determining the series Thevenin resistance. And this is step number 2. Here we just simply do this. We short the voltage sources and open current. And then stare into the resistance. There should be a comment. Look into the resistance of this terminal. So what that means is we take this power supply right here, which is a voltage source, and what do? We short it out. We simply act like it's not even there, and it's 0 volts across there. So what does that actually look like? So we replace the power supply with a short. Now, if it was a current supply, you would replace it with an open. That's the key thing. So for you open current sources, and then we find the open circuit resistance. So what we're doing is we're staring into these terminal, and we're looking for the resistance, as if you had an ohm meter and you're staring in it. So what does that end up looking like? Well, that looks like to me a parallel set of resistances. So we end up with R1 in parallel with R2. So let's take a look at that. What does that become? That becomes 5,000 over 150, because this is 500 times 100, because this is using the formula for 2 resistors in parallel, over the R1 plus R2, which is 150. So the formula for this, just as a reminder, is equal to R1 times R2 over R1 plus R2. And this all comes from the equation. Remember, the master equation for this is just 1 over R1 plus 1 over R2. And if this is in resistors in parallel, technically it's 1 to Rn, is equal to R equivalent. And that's where we're getting this. So now that we have that, we now have RT. So from the previous slide and this slide, the numbers agree. Using the short circuit method and solving for the short circuit current, we got 33 1/3 ohms. Using this method here, where I shorted out the power supply and then looked and stared and computed the resistance of this equivalent circuit and got effectively the Thevenin equivalent resistance just by solving for resistance values, we got 33 1/3 ohms. So clearly the same solution. So that leads us to the final step, which is drawing the actual circuit. So this is really important. I know it seems a little trivial that this would be the last step that we're going to talk about, but drawing the circuit is something that even on the test, when I have a Thevenin equivalent, because there will be a Thevenin equivalent on the test, You'll solve for VOC or VT, then you'll solve for RT, and you'll have the values. And historically, probably about a third of the class skips the last step, which is redrawing the circuit. So here we solved for VT, so we have our 5-volt resistor, our 5-volt power supply, and we have RT, which is our 33 1/3 ohm resistor. And that is it. That is our Thevenin equivalent circuit. So that simple voltage divider circuit we can regenerate and turn into an equivalent circuit that looks like this. So let's do another example. Here we have a 20 ohm and a 5 ohm with a 50-volt power supply. This here is very similar to obviously the circuit we just did. So the question is, what is VT? So VT in this case is going to be 50 volts times, we have here 5 ohms over 25 ohms, which ends up being, let me grab my calculator. Is that 5 over 25, which is 0.2 times 50, ends up being 10 volts. So that's VT. So RT, we can solve either way. I'm going to do it the short circuit way, or do it where we short circuit the power supply. So we do that, we end up with a 5 ohm in parallel with 20 ohm, which ends up being 5 times 20 over 25, which ends up being 4 ohms. And then you draw the circuit. Or the correct way to do it here. I usually label these terminals A and B. You end up with 4 ohm resistor here and 10 volt power supply here. Now is the Norton equivalent. So, well, what we just determined was the Thevenin equivalent, just to draw that again, was 10 volts and 4 ohms. So the Norton equivalent is now current supply with a Thevenin resistance in parallel, so there's a change in the circuit configuration. This is still 4 ohms. So what is the current? So we end up with 10 volts divided by 4 ohms. This happens to be 2.5 amps. So IT is equal to 10 volts over 4 ohms. So another useful thing about Thevenin equivalent is that there is a point in which the maximum power is transferred. And this is simply due to the fact that we have a resistance now that's in series, and we're going to attach some load, some device to this circuit, and we're going to drive that. So this load is what is being connected to the terminals of the Thevenin equivalent. So RT and VT are fixed, and so the question is, what is the maximum load that you can attach to the circuit to actually transfer the most power? So you're looking for a maximum at this point, a maximum value that you can get. So power in the load is simply about, remember, power is voltage times current. So that's what we're really looking for here. And we're looking for the maximizing RL, or what is the value of RL, what maximizes the power that it's going to do. So there's going to be a point where, like for instance, if RL is equal to 0, then there's going to be no power in the resistor. You're going to short out the supply, but there is going to be 0 power in the circuit itself because the load is 0 ohms. And obviously another extreme of that, if RL is infinity, like basically open circuit, there's no current flowing through RL at that point, so therefore also power is 0. So graph-wise, you're going to have just intuitively, and we'll show an actual graph here in a second, if happens to be in the units of RL, in ohms, if this is 0 and over here is infinity, at 0, and this is power, PL, the power going through the resistor. At one end, you're going to be at 0, and the other end is 0. So there's going to be some function. We don't know what it's going to look like. It could be squiggly, it could be smooth. As you're going to see, it's going to be fairly smooth. But there's going to be some sort of relationship that's obviously going to start out at 0, increase and go positive for power, because this is going to be an absorbing device. So it doesn't have negative power. It's a resistor. So it's going to increase in power, and then at some point, it's going to start decreasing. So we're going to take a look at what this formula is. So you can do the circuit analysis and easily figure this out, but I'm just going to show you real quick and show you what you really need to know. And when it comes to the test and in the material for the homework, and really the only thing you really need to know here is where is the point where it's maximum. Well, first of all, power in the load is determined simply because, remember, this is a voltage divider. And if we remember, our formula for power using voltages is V squared over R. So that's what's governing this equation right here, is V squared over R. So what is the power or the voltage across RL? Well, right now we've created a voltage divider circuit again, where RL is, if you will, R2 of the voltage divider. So we use the voltage divider formula. That gives us, if you will, the power across the load, or the voltage across the load. So VL, which would be this. And we got to square it. And so obviously you're going to end up with more of not really a parabola, but you obviously got the square term, so it's going to look a little parabola based, and divided by RL. So that's that. If you go through and take the maximum, if you look at this and find where the max where this peaks, it ends up occurring where RL and RT happens to be the same. So you will transfer the maximum amount of power in RL when RL is equal to RT. This is an important one to remember. And that looks like this. So here we have our circuit, and here we have at 4 ohms, because we determined in a previous circuit that RL T was equal to 4 ohms and RL is equal to 4 ohms, we have maximum power transfer. So in summary today, we discussed Thevenin equivalent circuits and the Norton equivalent circuits, where we took a complicated DC circuit that had power supplies, both voltage and current sources, multiple resistor stages, and turned them into, in the case of a Thevenin equivalent, a voltage source and a series resistance, and correspondingly with the Norton equivalent, current source with a parallel resistance. So turning it into a two-component circuit. As such, we also talked about what the load would be to enable maximum power transfer. Because of the series resistance in the case of the Thevenin equivalent, you would have to have the load resistor equal to the series RT for there to be a maximum power transfer, or the in parallel RT in the case of the Norton equivalent.